Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's show is Tour of the Universe in Open Space. And here to tell us all about it is Tim Campbell. Tim, welcome back to the show.
Thank you for having me back, Don. It's good to be here.
Yeah. Well, for our audience who may not know what is Open Space?
So OpenSpace is PC astronomy / planetarium software. There are a lot of planetariums that actually run this, but the software is developed in cooperation or sponsorship by NASA, and it's open source, it's free, and it turns out anyone can download this. You would go to openspaceproject.com, you can download it. It runs on Windows, it runs on Intel Macs. It doesn't run on the new ones because Apple dropped support for something called OpenGL, which it requires. It can also run on Linux, but it's completely free. And as I said, a lot of planetariums use this software.
Interesting. So we're going to be able to bring this to our guests on our program. So where do we begin?
So let's just start. We have the Earth just floating in space. I should mention that the texture maps that you see of Earth, those are actually pulled from a database from NASA. Somewhat real time when we do these planetarium shows. There are satellites in orbit constantly getting weather images, where the clouds are and things like that. And the texture maps are not necessarily real time, but I'd say within the last 24 hours.
As close as practical.
Pretty close. But what I want to do is start backing away from our solar system, and you can see the entire solar system out on the screen. And for years and years, we knew obviously that there's lots of other stars and lots of other galaxies, but we didn't know that there were lots of other solar systems. Our solar system was it. Of course, we suspected, but we had not yet actually confirmed it. So what's actually happened is we've now confirmed that there are exoplanets. The missions that did that were NASA's Kepler satellite that went up and started.
And that's what we're seeing on the screen right now.
Every one of these little blue bubbles that you see is the position of a star with at least one or more known planets. So Kepler was the first mission. That's a NASA mission. Kepler is not functional anymore. The new mission that took over for that is TESS. That's through the European Space Agency. TESS is an acronym for the Transiting Exoplanet Survey Satellite. Between the two of them, somewhat recently it was 4,000, but we've now upped that to 6,000. And what you're seeing on the screen are actually confirmed exoplanets. So there are multiple ways that we can check to make sure that it really is there. It's not just noise in the data. And as I back away more, we can start to spin around and see all of these things. So as I said, there's about 6,000 of them. This is not all of them. We'll get to the unconfirmed ones because we have those as well. There are many more. But what I would like to do is talk about something called the radiosphere.
Okay, well that sounds interesting. I'm sure it has something to do with radio.
It turns out it does. It's actually radio, traditional radio, like you would normally think. It's not a special sciencey word. So back in the late 1800s, we invented radio first. And the problem with radio in those days was that we had not yet invented an amplifier circuit. So that would come later, that we developed an amplifier. That then gets combined with the radio, and then we have radio and television broadcasts that are amplified.
And this is the sphere that we're looking at on the screen.
And so this sphere represents the distance that since the days when we have amplified the radio signal.
It's about the 1920s, I believe?
Yeah, probably 1920s, 1930s. That these signals have now been able to propagate through space. And you can see quite a few of the little blue bubbles inside the big blue sphere, meaning that if there is intelligent life on those planets and they know how to receive radio signals, they can watch our old television programs. So if you're near the outside of the sphere, toward the outer edge, you're watching the shows from, say, the 1940s, 1950s. If you're closer into the center, you're watching more recent things because it takes, of course, time to travel all those light years.
So in other words, it's the difference between watching I Love Lucy and the Brady Bunch.
Yes.
Okay.
So now we'll zoom out a little bit more, and I do want to turn on the unconfirmed exoplanets because there are an insane number of those. Let me see if I can just move this forward. And there you go. There are the unconfirmed exoplanets. So this huge scattering of all these green dots. I will call attention to that yellow cone shape that you see.
It looks like a jet of energy coming out of a black hole.
And that was because in Kepler-1 days, they were able to have that satellite stare in the same direction in space for ages and ages and ages, detecting as many exoplanets as they could. The way TESS works is TESS only looks at think of it as a tile of the sky for about a month, and then it goes on to the next one. Well, you have to get 3 orbits of 3 confirmed dimmings of the star with the same period between the first 2 and the second 2 to say, okay, that's a regular pattern. And so we were able to, with Kepler, hold it in one position for a long time. Eventually, they lost the ability to control the steering, and then they went to the Kepler-2 mission where they couldn't look in any particular spot for very long. So based on the quantity that you see in that yellow cone, imagine what we would detect if we had the ability to stay there for a very long time. So now we're showing the constellations. I currently have the labels turned on, so you can say, you know, there's Virgo and Libra and all the names of the various constellations going by. I'm going to turn those off because I want to do something interesting as we're tumbling around looking at the various points in the sky, and we're going to start to pull away from the planets. And this is something that I love to do in the planetarium when I do this for audiences, and they're always surprised by what we're able to show. So there we go. The labels are turned off. Let's go ahead and pull this out. And now you can see as we pull out, all of these constellation lines distort, and it looks like a huge, you know, like a huge asterisk, if you will. And that's because we see the sky as flat, but in fact, some of these stars are much closer and some of the stars are much farther away.
Our two-dimensional view versus the three-dimensional reality.
Yes. That's exactly what this is. And so if we now move ourselves away from our position in the Milky Way, hundreds, even thousands of light years, those same galaxy locations to somebody living someplace else, this is what they would see, right? Which doesn't make sense at all. So they only make really sense from our location in the galaxy.
Yeah, our vantage point on Earth, sure.
Yeah. We'll go out just a little bit more. And when we do this, now you see the entirety of the Milky Way galaxy, and notice all of those constellations are that little splat mark just off to the right side at about the 3 o'clock position in the center of your screen. That represents all of the familiar stars that you can see in the night sky when you go outside. So the most distant star that you can see, if you don't use a telescope, is a star named Rho Cassiopeia. That star is a yellow hypergiant, monstrously bright. Only 7 are known to exist. It's about 8,100 light years away. That's it. You have to have really good vision and in a really good dark sky. But the Milky Way galaxy is 100,000 light years across, we believe. And so if you would imagine comparing the galaxy to the size of the Detroit metropolitan area, all of the stars that you see would be within just a few blocks of your house.
Fascinating.
Right? You don't see it across the entire thing.
So everything is really pretty close to us relative to the size of even our own galaxy.
Yes. And so the the appreciation for how small we are, right, starts to sink in when you see everything that you think is familiar to you is just this little itty bitty piece, and you don't really see across the galaxy.
So we've been able to back away and take a look at the constellations that we're familiar with. So that'll be a good point to stop right here. If you have a question, please send us an email. The address, as always, is down at the bottom of your screen. And we'll be back with more of this conversation after Term of the Month with Stephen.
Thanks, Don. The term of the month is Artemis II. The 4-member Artemis II mission crew included Reed Wiseman, Victor Glover, and Christina Koch, as well as Jeremy Hansen from the Canadian Space Agency. They set the new record for farthest distance from the Earth, 406,000 kilometers, which is about 202,000 miles. The previous record was set by the Apollo 13 astronauts in 1970. While on the far side of the moon from the Earth, they got to see an Apollo 8-style Earthrise, as shown. The previous mission, Artemis 1, was unmanned. It tested many systems. The ablative heat shield showed a possible problem. The idea of an ablative heat shield is that during re-entry, hot bits of the shield burn off, taking heat with it. The re-entry profile had the capsule enter the Earth's atmosphere, aerodynamically curve back out of the atmosphere, and then re-enter the atmosphere to come down and splash down. However, the Artemis heat shield is different from Apollo, and on second entry, pockets of atmosphere filled small cracks. When it heated, bigger chunks of the shield came off than expected. For Artemis 2, this was addressed by performing a single steep entry. Analysis said it should work, but it didn't have to work. Now it has been tested. Artemis 2 tested much more with such things as life support and the new toilet. Artemis 2 splashed down April 10th near San Diego. The crew was safely retrieved. A quick health check, and all crew members are reported in good health. What's next? Artemis 3 will include an orbital rendezvous between a crewed Orion spacecraft and a human landing system, perhaps in 2027. After that, a descent and landing to the moon, perhaps in 2028. And that is term of the month, Artemis 2. Back to you, Don.
Thanks, Stephen. We're back with our guest, Tim Campbell, talking about the tour of the universe in open space. So where are we going next, Tim?
All right. So from our view of the Milky Way galaxy, we can now begin to pull out and go farther away. As we do this, you'll see things like the large and small Magellanic Clouds starting to drift by, but you're going to start to see these colorful dots appear. And these colorful dots in this scale do not represent stars. Each dot that you see in this image represents another galaxy. Now, these galaxies live in clusters of galaxies. They're usually not all on their own. Our galaxy group is called the local group. That's the imaginative name that they came up with. But you'll see lots of other galaxy clusters out here as we start to turn this around. This database of galaxies was put together by a guy named Brent Tully. And Brent Tully, or the Tully 3D database of galaxies, as we call it, came up with a database of galaxies. He decided to do it based on a cube. You would think it would be based on a sphere, but it's a cube. And the cube is 700 million light years on each side. We are precisely at the center of the cube. And he's mapped all of the galaxies inside this volume. And it turns out to be about 30,000 galaxies that are in here. And so we're obviously violating all known rules of general relativity by being able to zoom around the universe this quickly, but to give you an appreciation for how much stuff is out there. This is not all there is, though, right? This is just the Tully database. We can actually go out much, much farther than this if we want to. If we go out a little more, you can start to see lots of little clumps in the Tully data. These are the galaxy clusters that I was talking about.
And those are connected by filaments to other
filaments, yes.
clusters?
Think gravitationally, right? So things just sort of gravitationally connect. Our local group, for example, has two large clumps in it. One is all the satellite galaxies around the Milky Way. Our galaxy is one of the two largest galaxies in the local group. The other one is the Andromeda Galaxy and its satellites, but those combined create the local group. And these are the clumps that we're talking about 134 galaxies just in our galaxy cluster. That's from memory, I might be wrong. As we start zooming out even more, though, we come up to something called the Sloan Digital Sky Survey. Now, the Sloan survey goes out much, much, much farther. Now we're going out billions of light years to be able to do the Sloan survey. What I want you to notice in the Sloan data is these black bits.
Yeah, the two triangles of nothing.
Yeah.
Yeah.
And you're wondering, what is up with those, right? So to show you what's up with those, it works best if we zoom in as quickly as possible to get back to our own galaxy. And as we come in here comes our galaxy, you can now see our Milky Way galaxy and it's nearly edge on. And notice that the orientation of our galaxy in this edge on view is exactly aligned with those black wedges that you saw in the other image.
Okay.
So it turns out there's a lot of dust in our galaxy.
Yes, there is.
And the way I normally explain this to audiences is I want you to imagine that you are a blueberry, or you live on a blueberry, in a blueberry pancake. And if you look up, you can see the ceiling. And if you look down, you can see the plate or maybe the pan, right? But if you try to look sideways, all you see is pancake material, right? You can't see sideways. So we can look up through our galaxy, obviously on quite a degree of angles. We can look down, but if we try to look straight out the edge, now we have to see through the dust. And it turns out that's quite a challenge to do in astronomy. So astronomers have a term for this. They call this the zone of avoidance, meaning this is the zone that's hard to study because of all the dust and debris that's in space. So that's the Sloan data with the zone of avoidance that you see there. I could actually rotate this around. We can keep going out and you'll see more and more and more dots starting to appear. A lot of these red dots are the quasars. Quasar stands for quasi-stellar object. We detected them and thought, well, these seem like stars, but when they did the spectra, the redshift was insane. And when they looked at the redshift, they realized that the spectra was shifted over so far, they thought, what kind of star could be visible from such a distance? We now know that those are actually active galactic nuclei, black holes feeding on the matter around them, glowing super brightly.
Okay. So what have we arrived at here?
So now we've gone all the way out to something called the cosmic microwave background. And it goes something like this. If we now know that all the galaxies are receding away from us, then that means they must have been closer last year and the year before that. How many last years do you go to before everything must have been jammed very tightly together? And how hot would the universe have needed to have been to do that? It turns out when you get to a point that is within 380,000 years of the Big Bang, the universe is so hot that protons and electrons cannot combine. They can't get together and form ordinary atoms like we have on the periodic table. They exist, they just don't combine. At 380,000 years, the universe finally cools, and that can happen, and we get hydrogen and helium and a trace amount of lithium. But this is the image that we were able to capture. It was discovered by two guys that worked for Bell Labs that were trying to bounce radio signals off of satellites for long-distance communication, and they kept getting this noise, this persistent noise, and it was everywhere. They thought their equipment was defective. They tried to do everything. They were scrubbing pigeon droppings off of their radio dish, thinking that was responsible for the noise. It turns out they had detected the echo of the cosmic microwave background. Now, the universe is ionized at this point, so we can't see beyond this. But this is as far as it's possible to look in the visible universe. There's a known universe that is larger than this, but this is the limit of the visible universe. This is how we get to that number where we say the universe is about 13.8 billion years old. Mm-hmm. This is how we get to that. This particular image that you're looking at was captured by something called the Planck satellite. The first one was something called COBE, the Cosmic Background Explorer. The second one was higher resolution. It was called WMAP, the Wilkinson Microwave Anisotropy Probe, so say that 10 times fast. And the third one was Planck, and Planck is actually not an acronym, that's the man's name. So this is the Planck data, and the hot bits are red and the cold bits are blue. But the difference in temperature between the hot bits and the blue bits and the cold bits, right, is about 1 part in 100,000 of a single degree in Celsius.
So for our purposes, for us, it's
almost exactly uniform temperature all the way around,
would be negligible.
which is kind of impressive. Another thing that's kind of fascinating about this is we live at a time when the universe is less than 15 billion years old. I want you to imagine a time when the universe is at least 10 times older than it is now, 150 billion years old. Well, what should happen? the Andromeda Galaxy and the Milky Way galaxy will have combined, and the satellite galaxies along with it. The galaxies that are not part of our local group, they will have moved off to a point where they are beyond the cosmic horizon. They are receding away from us faster than the speed of light. It is not possible to see them anymore. And the cosmic microwave background will have cooled. This is, by the way, about 3 degrees above absolute zero, about 3 degrees Kelvin. It will have cooled to undetectable levels. This means that if you are a cosmologist living in this distant, distant, distant future, and you try to study the origins of the universe, the evidence that you need is gone. You have no evidence of other galaxies, and you have no evidence of a cosmic microwave background. So we live in a very unique time that we are actually able to detect this. So this is essentially the end of the universe. For funsies, I can talk about one other object if you think we have time.
I think we have a couple of minutes. Go ahead.
All right. So each year, the Webb Space Telescope, this is the instrument that is imaging the universe in infrared. We've talked about this before because the wavelength of light has stretched so much that it is well beyond the visible spectrum. So it's imaging in the infrared. It is able to image pretty much all the way back to the cosmic microwave background. The most distant galaxy that it has detected, I think this is within the past year, is an object called MOM-Z14, MOM-Z14. The 14 is a rounded value, and the Z in front of the 14 means this is the term that astronomers use to talk about redshift. So if I have a wavelength of light that's, say, 500 nanometers, and I stretch it to 1,000, so a factor of 1, greater than what it is, that's a redshift of 1. I do another 500, that's a redshift of 2. This is stretched more than 14 times the original wavelength. It's actually stretched 14.44 times. That translates to a galaxy that is 280 million years after the Big Bang. It is more than 13.5 billion light years away. It is receding away from us at 99.2% of the speed of light, which is just staggering to think about. And we can do a little bit of math. I talked about this is the limits of the visible universe. We have something called the known universe, which is bigger. And that says, well, if the light we're receiving from it left 13.5 billion years ago, that's where it was then. Where is it now? And when you do that math, it turns out that it's a little over 33 billion light years away. So this is how we come up with this idea that there is a visible universe and something called a known universe, which is even bigger still. And then there's something called the whole universe, which is how big can you go? We don't know the answer to that question.
This whole thought here gives a whole new meaning to the idea of the raisin bread that's left to expand over time, and that's a big loaf of raisin bread.
It is a big loaf of raisin bread. So normally when we do planetarium shows, people love to see the planets and the moons and things like that. I thought this time it would be exciting to leave the solar system behind and go out and look at the entire universe.
To boldly go, as they say. Tim, I want to thank you so much for coming in to be able to show this and explain it to our viewers. Please visit our club website. The address is down there at the bottom of the screen, as always. And coming up next is What's Up with Stephen.
Thanks, Don. What's up in the night sky for May 2026? The sun goes from Aries to Taurus this month, with Venus, Mercury, Mars, Saturn, and Neptune close by. The month of May starts with a full moon on the 1st. But it's apogee, or close to it, so this is a small moon, a small full moon. Last quarter is the 9th, new moon is the 16th, first quarter is the 23rd, and the full moon again is on the 31st. So we have another apogee even closer this time to the full moon, so we have a super small blue moon. So then we see Mars, Mercury, Saturn, Neptune, and Pluto. Mercury is in Pisces and goes to Taurus over the month, and it rises a half hour before sunrise to setting an hour after sunset. And that's because we have superior conjunction on May 14th. We also have perihelion on May 18th, so Mercury is physically closer to the sun, so it's visibly closer to the sun in the sky most of the month. Mars goes from Pisces to Aries and rises an hour to 2.5 hours before sunrise. Saturn is in Cetus and rises an hour to 3 hours before sunrise. Neptune is in Pisces and rises an hour and a half to 3 hours before sunrise. And Pluto is in Capricornus, rising 3 hours to 5 hours before sunrise. Pluto is actually getting doable far enough away from the sun that if you get up in the, in the wee hours of the morning with a sizable telescope, over 10 inches, I think, and you could get, or you could do photography and get a shot of Pluto. And it would be cool. Then we have Jupiter, Venus, and Uranus. Jupiter is in Gemini and sets 5 hours before sunrise to 6 hours before sunrise. Venus goes from Taurus to Gemini and sets an hour and a half after sunset to 2.5 hours after sunset. Perihelion on May 14th, so it's also closer to the sun than you'd expect. Uranus is in Taurus and sets sunset after plus 2 hours, but then rises half an hour before sunrise, and that's because superior conjunction for Uranus is May 22nd. Then we have Comet Pan-STARRS. Comet Pan-STARRS was naked eye, magnitude 4.7 on April 19th, and was in Taurus going to Eridanus May 1st through Orion May 15th, and close to Sirius and Canis Major by end of month. Now, it gets closer to the sun, so it's harder to see as the month progresses, so it should be better from the southern hemisphere later in the month, and the comet itself could reach magnitude 0 or even negative over the month. It could be spectacular. And that is what's up in the night sky for May 2026. Remember, we don't charge money for this show, but we may tax your brain.